All right, so I believe this is recording. Let's take a look at this problem 3. They give us two functions f and g. They are both rational functions. We see ratios, we see variables in the denominator. And they're going to ask us like 9 different things to do with these two functions. So let's start with a, b, and c. They're asking us to build a new function in part a through subtraction, in part b through multiplication, and part c through division. So fortunately, for these rational functions, it's going to be a lot easier on us because they have the same denominator. Each of the denominator is x minus 3. So for subtracting these, I know I can write this underneath the denominator x minus 3, and I can take x, which is the numerator of f, and subtract the numerator of g. So this new function, f minus g of x, I could have given it any title that I want. I could have called it h or q or any letter. But f minus g was a nice title because it tells us how to construct, how to get this new function. In the numerator, x minus x cancels, and don't forget to distribute the negative sign to that second term. So this is the expression we get for part A. This is the new function that you get when you subtract f minus g. All right. What if we took f and g and divided it, or multiplied them together? It would create a new function. So, multiplying these two functions together, we have g is x plus 1 over x minus 3, and f is x over x minus 3. So when to multiply, we just multiply straight across the numerator and straight across in the denominator. So we distribute this x to both terms. In the numerator, we get x squared plus x. And in the denominator, when you multiply these two binomials, you get x squared minus 6x plus 9. And we can't simplify that any further, so that's our final answer. In part C, they want us to build a new function by dividing these two functions. Well, students sometimes have a little bit of difficulty here because this is creating a complex fraction, a fraction within a fraction. See, the function g itself is a ratio, is x plus 1 over x minus 3. And f itself is a fraction, x over x minus 3. But students sometimes remember what to do here. If instead of writing this as a complex fraction, remember that this division bar, this represents division, so I could have chosen to write this as x plus 1 over x minus 3 divided by x over x minus 3. Because seeing it in this notation, in this form, jogs a lot of students' memories a little bit better, and they remember that division is the same thing as multiplying by the reciprocal. So if we change this division to multiplication, we have to flip this fraction. We have to take its reciprocal, x minus 3 over x. And we see now when we multiply these together that we have a common factor in the numerator and denominator that just divides to 1. So this new function, g divided by f, we could have called it h or something, but this gives us a clue as to how it was constructed, because now once we simplify it, we've lost a little bit of detail of how it was made. You know, there's no way that we could have done this division if certain things were allowed to be true. If x were allowed to be 0 or if x were allowed to be 3, this would not simplify to this. And that's what we're going to do next in parts D, E, and F, is find the domain for each of these expressions. And like I say, just simply looking at this reduced expression, you're going to lose information if you don't consider the domain of f, the domain of g, and think about how this function was built, how it was constructed. All right, so there's our final answers for A, B, and C. I'm going to erase this to find the domains, because even though it's nice sometimes to have the expression, I don't need these expressions to find their domains, because I have f and g, and I can figure out the domain of f and domain of g and use that to figure out the domains for this parts A, B, and C. All right. So to find the domain, of f minus g, we find the domain of f and intersect it with the domain of g. And we do the same thing for g times f. We find the domain of f, the domain of g, and intersect the two. So part D and E will always have the same answer. Part F might have the same answer, but it could have an additional restriction, because in the denominator there is the function f, and we can't have division by 0, so we may have to throw some numbers out of the domain that cause f to be 0. And the same is true for J. It might be the same answer as D and E, but we might have to add an additional restriction, because not only do we have to intersect the domains of f and g, we have to make sure that g is never equal to 0, since it's in a denominator. All right, so let's begin by finding the domain of f and the domain of g. For the domain of f, the domain is a set of all real numbers, excluding any values that cause division by 0 and excluding any values that cause us to take the square root of a negative number. We don't have any square roots. We don't have to worry about that. We do have a variable in the denominator, so we have to avoid the number 3, because 3 minus 3 gives us a 0. So the domain for f is all real numbers, excluding the number 3. And the domain of g, well, it's the same. It has the same denominator. So it's all real numbers, excluding the number 3. So when we intersect these two sets, to be in the intersection, to find the domain of f minus g, is this going to be the same answer as the domain of f times g, because you take the domain of f and you intersect it with the domain of g. To be in the intersection, you have to be in both sets. So, since they're the same, however, the answer that we get from negative infinity to positive 3 is in both sets. 3 is not in both sets. Actually, 3 is not in either one. So for D and E, we get the same answer that we got for the domain of f and domain of g. So far, all these domains have the same answer. But that may not be true for the rest of the problem. Could be, could not be. When we find the domain of this division, it's still the domain of f intersected with the domain of g, but we also have the added restriction that this f of x cannot equal 0. So what is f? Well, f is this ratio x over x minus 3. And I claim that when a fraction does reduce to 0, it's because the numerator, because the denominator can never be 0. So if x were allowed to equal 0, then f evaluated at 0 is 0. We don't want that to happen, so we're going to have to throw 0 out of the domain. We've already thrown out the number 3. Now we have the additional restriction to throw out the number 0. So the domain for g divided by f is from negative infinity up to 0, excluding 0, up to 3, excluding 3, all the way up to positive infinity. So there's our domain for g over f. What about the domain for f over g? This time, g of x is in the denominator, and we can't have g of x equaling 0. We know the answer for this is going to be the answer that we got in D and E, plus any additional restriction that if there's a solution to the equation g of x equals 0, we're going to have to throw out that value of x. Well, g of x is this ratio x plus 1 over x minus 3. And if a fraction reduces to 0, it's because the numerator, the denominator, can never be 0. So if x were allowed to equal negative 1, g evaluated at negative 1 is equal to 0. We don't want that to happen, so we have to throw out negative 1 from the domain. So we've already thrown 3 out, and now we have to throw negative 1 out. So the domain, see, that the 0 that we threw out, it's okay now for that 0 to be in the numerator. We don't have to use our answer in part f to help us with g. We have to use the answer in part D and E along with this added restriction that the denominator can't be 0. So the domain for f over g is all real numbers excluding negative 1 and excluding positive 3. All right, so for these 4, there's our 4 answers. For D and E, it was all real numbers excluding positive 3. For F, it was all real numbers excluding 0 and positive 3. And for this J, it was all real numbers excluding negative 1 and positive 3. All right, so I hope that helped. Now let's take a look at these last 2. So I'm going to need to erase all this. I'm not going to erase the domain of f and g because I'm going to use that when I build these new functions to find their domains for this next problem, the next parts. All right, so I want to find the domain of this composition, g composed with f. And then I want to find the domain. This happens to be the same. This must be a typo, so I'll have to change one to, we're going to do f, the domain of f composed with g. All right, so in L, in part L, we want to find the domain of f composed with g. All right, so let's think about how this function composition, how this new function is built. I don't necessarily need the equation, but I do have to consider how it was built, how it was constructed. So the first function that's applied is the function f, and then it's like an assembly line. Then we apply the function g. So two things have to be true in order to get an output. X has to be in the domain of f, otherwise we would have no output here, f of x. And f of x has to be in the domain of g, or otherwise we wouldn't have an output here. All right, so we have the domain of f and the domain of g. They're all real numbers excluding 3. So I'm just going to write shorthand notation here that x can equal 3. So over here what I need to do is this f of x, I need to temporarily let it equal 3 so I know what number to avoid here that produces an output of 3, because g can't receive an input of 3. All right, so this function f is x over x minus 3. So I need to solve this equation. Let's cross multiply. Let's add 9 to each side and then subtract 1x so that I have 9 is equal to 2x, or the x is equal to half of 9. So what this tells me is that if you input 9 halves into f, the output will be 3. And we do not want that to happen, because if you give 3 into g, that output is undefined. So in order to prevent this undefined, we have to prevent 9 halves from being in the domain of f. It's not that f has a problem with it. It's that once f does its magic, does its rule, the output is 3, and g can't handle 3 because 3 causes division by 0. So we're going to have to throw out 9 halves from the domain. And that's 4.5, right? So what do we have? Well, for the domain of this composition, let's shrink this up so we can write it. I don't need to shrink up that part L. So the domain of this function composition, g composed with f, is the set of all real numbers. But we have to exclude the number 3, and we have to exclude the number 4.5. I'm just going to write it as 9 halves. As long as we pick any number that's in the domain, we'll have an output for f, and then when that becomes the input for g, we have a final output for g, and that's what we need to happen. All right, so let's shrink this up. I really don't need this answer for the next problem, but I'm just going to leave it here, just so that you can see for comparison. Let's change colors to blue here. So this time, I think of the order that I'm applying of my functions here, my assembly line, has changed. That g is now being applied first, and then the output of g is becoming the input for f. And the output of f is our final answer. So two things have to be true in order for an input into g to have an output out here of f. X has to be in the domain of g. So x can't be the number 3. And this g of x has to be in the domain of f, which means the output for g cannot be 3. So we have to figure out, we have to temporarily let this equal 3. And g of x, remember, is x plus 1 over x minus 3. We have to find the solution to this equation and then make sure that we throw that out of the domain. So we have a proportion. So let's solve this proportion by cross multiplying. So along one diagonal, I have x plus 1 times 1. And along the other diagonal, I have 3 times this binomial. And 3 times x minus 3, I'm going to go ahead and distribute it also, as 3x minus 9. So let's take away x from each side. Let's add 9 to each side. And let's divide by 2. So what does this tell us? Well, this tells us that if you allow 5 to be the input for g, what will happen? Well, if we allow 5 to be the input for g, the output will be 3. And when we allow 3 to be the input to f, we have an output that is undefined. So 5 isn't related to any output, so therefore 5 can't be in the domain. So we have to throw 5 out of the domain. Now remember, we've already thrown 3 out of the domain, so now we have to also throw 5 out of the domain, and we'll have our answer. The set of all real numbers, excluding 3, and also excluding 5. Written in interval notation, this domain of f composed with g is the set of all real numbers, excluding the number 3, excluding the number 5, but everything else is okay. So there's our final answers for K and L. Remember, I'll correct that. I don't think that you'll ever see that typo. Hopefully you won't. I'll remember to correct it on the worksheet. So I hope this helps. Ask any questions as needed, and I'll talk to you later. Bye.